Lots of people have good ideas. I heard a story one time that a young student was at a university get-together. He kept pulling out a small notepad and writing things down. One of the lecturers asked him, "What are you writing on that?" The student said that every time he had a good idea, he would jot it down. The lecturer, who happened to be Albert Einstein, said, "That wouldn't work for me. I've only had a few." Welcome to the Terran Space Academy. I would like to take a moment to thank all of our patrons who are helping us continue our work to help prepare you for a bright future in the space industry. One of those few ideas that Einstein humbly mentioned had been written in 1917 and concerned the quantum theory of radiation. Scientists at that time were puzzled that there seemed to be specific peaks and gaps in the photon emission spectrum of elements. The hydrogen spectrum looked like this, and here is helium. Helium was, in fact, first recognized in light coming from the sun, before it was isolated and identified on Earth. Photons can be created of almost any wavelength. Wavelength and frequency are inversely related. As the wavelength gets smaller, the frequency gets higher. That's because the speed of light equals the wavelength times the frequency. As one goes up, the other must go down, and vice versa. If we look at an oscillating wave, like the one here, we measure the wavelength from peak to peak or trough to trough. Wavelength is usually given in nanometers for visible light. Some scientists, including doctors, use wavelength to describe light. The frequency is the number of waves passing a given point over a specified period of time. Physicists often describe photons by their frequency. Frequency is measured in hertz, or events per second. Now that you have this equation, you can quickly convert one to the other. But using frequency can be useful. If you know the frequency of a photon, you can use this equation, called the Planck-Einstein energy-frequency relation, where E equals h nu. H stands for Planck's constant, and nu stands for the frequency. Planck's constant is 6.626 times 10 to the minus 34 joules per hertz. This lets us compare the energy of, say, blue light with a wavelength of 470 nanometers with red light that has a wavelength around 650 nanometers. Since we have been given the wavelengths, we can use the first equation to find the frequency. Let's start with the blue light. The speed of light divided by 470 nanometers gives us 6.38 times 10 to the 17th hertz. Now to find its energy. Multiply Planck's constant by the frequency, and we get 4.23 times 10 to the minus 16 joules. Not a lot of energy for just one photon. Now let's look at the red light. A wavelength of 650 nanometers divided into the speed of light gives us 4.61 times 10 to the 17th power. Multiply this by Planck's constant, and we get 3.06 times 10 to the minus 16 joules. This shows us that the red photon has only 72% as much energy as the blue photon. If we go to higher frequencies, and therefore higher energies above blue, we move into indigo, violet, and ultraviolet. Ultraviolet light has a wavelength of 400 to 10 nanometers and can cause skin cancer. It is the lowest frequency of light that can normally ionize atoms, though concentrated radio waves can be used to ionize gas under the right conditions. Above ultraviolet light, we get X-rays, with a wavelength of 10 nanometers to 10 picometers. The frequency of a 10 picometer photon would be 3 times 10 to the 22nd hertz. The energy would be 1.99 times 10 to the minus 11 joules, and this is 65,000 times more powerful than our red light photon. The highest frequency light that we have a name for is called a gamma ray photon. The most powerful gamma ray ever detected had an energy of 7.2 times 10 to the minus 5th joules. That gives it a frequency of 1.09 times 10 to the 29th hertz and a wavelength of only 2.76 attometers. An attometer is 1 meter times 10 to the minus 18. This gamma photon was 236 billion times the energy of our red light photon. Particles with this much energy are usually created in our universe by supernova and black holes. The wavelength of a photon can also be very long. Below red light we find infrared, and at even lower frequencies we get microwaves, which have a frequency of 3 times 10 to the 8th hertz. We would call this 300 megahertz, to 3 times 10 to the 11th hertz. We would call this 300 gigahertz. Why do we use such weak photons to heat our food? Microwaves happen to be the frequency of light that hydrogen absorbs. By bombarding our food with microwaves, we cause the hydrogen atoms in the food to absorb photons, gaining energy. This gain of energy increases molecular motion, and the kinetic energy of molecules and atoms is what we call heat. By the way, the wavelength of the microwaves in your oven are around 12 centimeters, or about 4.7 inches for my American friends. And you guys in Liberia, too. Way to hold out. Radio waves have even longer wavelengths. Household current in America is about 60 hertz. These wires create a radio wave with a wavelength of about 50,000 kilometers. The frequency of light is limited by the power necessary to create it, and the wavelength by the size of the universe. By the way, if we ever detect a bright spot of gamma photons with a frequency of about 123.6 terahertz that are redshifting, someone is coming to visit with an antimatter engine, and they are slowing down to say hi. Now that we understand about photons, let's go back to Einstein, and a problem that has existed for a long time. Who gets credit for an idea? The person who thought of it, or the one who builds it? In 1917, Albert Einstein said the electron shells around atoms don't look like this. They look like this. This shows that there are specific energy levels that the electron can stay in. The formula for the number of electrons in a shell is 2n squared. So shell 1 can hold 2 electrons, shell 2 can hold 8, shell 3 can hold 18, and so on. When we fire photons at an atom, like hydrogen or helium, the photon can hit one of these electrons and make it jump to a higher energy state. The electron will then jump back down. When it does, it gives off a photon, giving up the extra energy. But while the photons that hit the electrons can have any energy level, these shells limit the energy change of the electrons as they jump down by an exact amount. This will cause the photon they give off to always be a specific energy. Einstein thought that if you pulsed a concentrated burst of light at the right atoms, they could absorb these random photons, and then give off light of exactly one wavelength. Not only would all the photons be the same color, but the wave patterns would all be synchronized. We describe this monochromatic synchronized light as being coherent. It took 36 years for anyone to build this device. In 1953, at Columbia University, a team of scientists created the first artificial beam of coherent light. This was in the microwave range. I say the first artificial beam of coherent light because rarefied gas in space will sometimes absorb photons and give off maser light also. The maser at Columbia used ammonia gas and created a 24 gigahertz beam. Masers aren't usually very powerful, but they are still used as timers in atomic clocks and as amplifiers in radio telescopes. They are also used for deep space communication. Because the light beam is coherent, it doesn't spread out as much as random light, allowing a lower energy to create a detectable signal over a great distance. Masers can now be designed to generate radio and infrared frequencies also. These are usually still called masers. Then in 1957, a visible coherent light device was created. At first this was called the optical maser, but that was just silly. Finally they decided on the acronym light amplification by the stimulated emission of radiation. This is a laser we all use in our pointers and printers. Lasers can be made very powerful now. The United States Navy has created lasers powerful enough to bring down enemy missiles and aircraft. On its way to Mars, Starship will probably have a maser device to communicate back to Earth. They may also carry a variant of the military laser for defense. Not from Martians, but from meteorites. Anything moving above about 300 meters per second at sea level will be supersonic. A bullet fired from a high-powered sniper rifle, like a 50 caliber BMG, will be far above that, at about 840 meters per second. This has a devastating impact on whatever it hits. We saw what a piece of frozen foam moving at high speed could do to a spaceship when one punched a hole in the wing of the Columbia Space Shuttle. causing it to come apart on re-entry, killing everyone on board. Now, a 5mm thick stainless steel starship is much stronger than the space shuttle. It could probably survive small arms fire without significant damage. A micrometeorite in space will have a mass of only up to 1 gram, but they can impact with a velocity of more than 10,000 meters per second. These have caused significant damage to the International Space Station, despite it having a ballistic fabric and Whipple shielding. A Whipple Shield is named for Professor Fred Whipple. It is a thin layer of material with a space in front of the protected surface. The meteorite will impact this shield and usually break apart, expending a lot of its kinetic energy. But Starship won't have a Whipple Shield as far as we know. And not all meteorites are micro. This is a solid chunk of metal, found where it had impacted the moon. One of these hitting the Starship at high speed would cause catastrophic damage. It is very likely that Starship will be scanning the space it travels through, with radar and LiDAR. It will take evasive maneuvers to avoid an impact if at all possible, but it won't be easy to throw something this massive out of the way quickly. The stronger your radar pulses, the further out you can see. I told you before that masers are pretty weak. No one had made one with much power, despite 70 years of trying, until recently. Professor Oxborough, a physicist at the National Physical Laboratory in the United Kingdom, on a tiny budget, created a maser 100 million times more powerful than anything created before. How he accomplished this is interesting, and an important lesson about the value of theoretical and applied physics. Professor Oxborough read a paper written in 2002 by 3 Japanese scientists, Takeda, Takegoshi, and Tadao. Most masers use a crystal like ruby to generate the coherent light. They pulse a bright burst of random light around the crystal and get a pulse of coherent light out. Ruby is composed mainly of aluminum oxide, and so is sapphire. That's the invisible metal that Scotty sold to a company in 1980's San Francisco. It's also what the Cybertruck windows are made of. Add trace amounts of iron, titanium, chromium, or vanadium to this transparent crystal, and you get a gemstone. I said before that most masers use rubies, and that these are inefficient. Other masers have been made that are more powerful, but they must be kept in a vacuum or cooled to very low temperatures. The scientists in Japan suggested that a very different type of crystal would work better. They suggested something called p-terphenyl doped with pentacene might work at room temperature without a vacuum. But that was 2002. It wasn't until a decade later, in 2012, that Professor Oxborough came across the article and built the device. What can we do with masers 100 million times more powerful than anything created before? Think of all the ways we use lasers today, and understand that when it was invented, no one could immediately think of a use for it. Now this super powerful maser can be used for deep space communications, and for what we will call MIDAR instead of radar. Radar stands for radio detection and ranging. MIDAR will be microwave detection and ranging. A MIDAR scanning system would need a lot less power than LiDAR, and be much more precise than radar. The other benefit is that the maser can be used to ablate the outside of an approaching meteorite, creating a jet of debris that will change its course. 3 powerful masers, attached 120 degrees apart on the Starship, should be able to scan and fire in every direction, ensuring a safe voyage to the new world. Thanks for listening. Don't forget to like and subscribe, and help us out on Patreon or at the Academy store. There are links in the description. Stay safe at Astra Pro Terra.